So far, we mostly looked at learning algorithms based on a couple of different ideas. The first one was the idea of minimizing the empirical risk of your data based on some given loss function, or some chosen loss function, possibly regularized, and then using techniques we've seen either linear systems in the case of least squares, and more generally first-order methods for more general loss functions. Okay. These are examples of what you might call the batch learning algorithm that process the data all at once. Okay? So if you get new data, you would have to retrain the model. So what we want to look at today is a situation where we want the algorithm to somewhat adapt as you get more data in, okay, without recomputing things from scratch. We're going to discuss a couple of different situations where these might be of interest. Okay? The first one is when data are actually coming in streaming. Okay, you get data batches at the time, and you don't want to just recompute everything from scratch, retraining everything from scratch all the time. This is the situation for many kind of real life data. Many of them don't satisfy the IID assumption that we've been making so far. The other situation is where data do not necessarily come streaming. They may be sitting on your laptop or desktop or GPU server somewhere, but they're a lot. Okay, they're so big that they don't fit the memory that you have at disposal. And at that point, it's not that much that data are streaming themselves. It's the emphasis on the idea that you want to stream the data somehow. You want to read them in chunks because you want to do because you have to deal with them, and you cannot just put them all in memory at once. Okay, this is, I mean, at least as important as the first situation. In many of real data sets that we're dealing with these days, they're so big that you cannot just put them all in memory. Okay. And here today is so this is a topic that as all the topics we've been seeing so far, one can discuss at length. We're just going to give a couple of snapshots of different ideas. Okay. So the keyword that we're going to use is online learning, and you can use this couple of words to refer to a number of different situations. Okay, in particular, you can put the emphasis on the problem or the algorithm. The problem can be online in the sense the data arrive some at the time. Okay, and here already this question you can recognize in different as appearing in different part of different way of one can make this idea of data streaming precise in a number of different ways. You can just assume data to be IID and come in a sequence. You can assume like time series model, okay, where data come in a sequence, they are stationary, but they're not independent. But you can also consider a situation where in some sense there is a finite horizon during which you receive data, you receive a sequence of data, but you don't make any modeling assumption the way the data are produced. This is somewhat more similar to a game theoretic perspective. So it is sometimes called sequential prediction. We're not going to deal with very much with this more modeling perspective. We take more of an algorithmic point of view. So the emphasis is on how the algorithm processes the data. So if you want, we could add this subtitle. Okay. Online learning algorithms is the algorithm itself that no matter how you get the data, wants to process it a bit at a time. What we've seen so far doesn't do it. Okay. We've seen essentially ERMs, methods based on the minimization of an empirical risk given by some loss function, possibly regularized. And then, okay, so up to when do you see in the back? Like here?
Okay, can't see.
But here's fine. Chaush. Chowish. All right. So remind me because I might forget in the agitation of writing stuff on the board. So, and then we have seen, let me call it GD or gradient, or let's say GM, gradient methods the latter compute a solution by doing an iteration, which is wt minus gamma t, and then some vector gt, and we have seen a couple of different situations. Okay, L differentiable. Then we can take gt equal to the gradient. Okay, let me give a name to this whole thing. Let me call this whole thing L hat lambda w, is the regularized empirical risk. Then we can take gt to be the gradient of the regularized empirical risk at the current iteration. Okay, this is the basic gradient descent iteration. In which case we can take gamma t to be a constant. The other case is with L is just convex, not differentiable, and then we can take gt to be an element of the subgradient of the regularized empirical risk. Okay, and in this case we need to take gamma t to be some kind of decaying sequence. Okay, for example, going down as 1 over square root of t. Okay. Okay, so that makes sense? So far, so good? These are basically the main ideas that we introduced last time. We only dealt with linear models. We then jumped to nonlinear extension using feature maps or using kernels. And in the process, we proved a number of representer theorems. Okay, in the P-set, you're gonna be asked to prove as an exercise the representer theorem, the one that is more common. We generally call representer theorems all the results that show that the W can be written as a linear combination of the input points, because this immediately gives a reparametrization of the W that paves the way to using kernels. Okay, and if you remember, in the process of discussing this, we proved a number of these results. Again, W or Wt equal xi cti, where these are the input turning points, and these are some suitable coefficients, and we actually provided a way to compute them based on this. Okay. Now what we want to do is to consider a situation where, again, the data might be, we want to process the data some at the time, not all at once. Okay? Here, at least from what we discussed, we use at every step of each of these methods, we use all the data. Okay? Now, if I give you one extra point, what do? Okay? At least in this framework, what you seem to have to be doing is recompute everything from scratch. Okay? You have to put the extra point in here. Then you have to compute a new gradient. And then I guess you could use what you computed so far to initialize a new gradient, but there is no real guarantee. Well, intuitively, this is going to work. Okay, it has to work. You're already closer to the solution. But it is not the canonical thing to do. And it's not really clear what are the kind of guarantees you can put on this solution. So what we want to do is to consider more systematically the idea of updating your solution as the data arrives. And as we've done before, we're going to use first least squares as a simple playground where you can derive a simple equation. And we're going to introduce the basic, one of the most classical ideas, which is the recursive least squares algorithm. Largely as an excuse to use a couple of linear algebra trick and useful equations, and then we move on and introduce stochastic gradients, and we try to make sense of why stochastic gradient is useful and in which kind of situation it is used, because there are a bunch of different perspectives on how and when to use stochastic gradients. Any questions about all this stuff? So what we want to do is to consider recursive least squares. Okay. Let me give a name to this. So let's call W hat lambda the regularized minimizer. And if you remember, we've seen that this can be written as X transpose X plus lambda n identity minus 1 X transpose Y hat. Okay? This is the n by d data matrix, and this is the n by 1 vector of outputs. Each row of that is an input point, each column is a dimension. Okay? We want to use the following compact notation. We want to introduce the matrix sigma n, which is simply this thing here, okay? Is the covariance matrix of your data, or the second moment matrix of your data, shifted by lambda n. Clearly depends on lambda, okay? But we don't care about this dependence. We want to emphasize the dependence on the cardinality of the data sets, because we will want to go from n to n plus 1, and then so on and so forth, okay? So this is the reason of this notation. Yes?
Lambda n, like n is the index for lambda, right?
Say it again?
Like n is index for lambda. Or is it like...
No, this is a...
It's a scalar.
Yeah, it is more or less, I don't know, it was in the right place. It is not an index of lambda. It basically comes from this. Okay? That's it. It just comes from this 1 over n. If you remember that, that's how it appeared. Okay? Okay? So here is the iteration that gives rise to the recursively squares algorithm. Is going to be the following. So look at this second line first. Okay? It looks a little bit like the gradient descent iteration for least squares. Okay? But what you have is that it only has just a second. So let me do it the same way I did it in the notes, otherwise I get confused between the two. So what we're going to do is that we're going to just assume that lambda is equal to 0. Okay? We just drop it from the notation. We're just going to work it, assuming that the covariance matrix is always invertible. Okay? And then otherwise you just have to change the notation a little bit. Okay? So that's the minor point. So for now, the main point we want to make right now is that if you look at this line here, this looks like the gradient descent on the least squares with a couple of differences. The first difference is that here you don't have the gradient, which would be x transpose x, xw's minus y. Oh, I might be screwing up the sign. Okay, this would be the gradient of the least squares. You can, because least square is just s transpose w minus y. What it is that we replace the matrix by 1 point, just 1 point. That's what's written here. Okay, just one row of the matrix. That's difference 1. Difference 2 is that in classical gradient descent, what you do here is to use some scalar valued step size. Whereas here, the step size is a matrix, for which we provide an update rule too. Okay? Now, this is a first example. So one question is how you derive this algorithm. And again, we're going to do the derivation quickly because it's not so complicated and it's somewhat instructive. But the observation is that this is an online learning algorithm in the sense that as soon as you give me a new point, I'm going to compute a new solution just by putting it inside this equation. You don't give me any point, I don't do anything. That's my solution. You give me a new point and I update the solution. Okay? The difference is really clear comparing to this would be a batch gradient. This is an online gradient. Okay? Or stochastic in the measure in which you just have access to a small piece of the total gradient. Okay? We're going to be more precise in a minute. Does that make sense? Yep.
But this is different from, I mean, if you write the recursive relation to the end, do we obtain necessarily the same gradient of both?
We don't know because we haven't derived. I'm going to prove to you that this is the same as this.
It's exactly the same.
Yes. Yeah. So the question was, if I run this, would I get the same as this? Okay. And again, we're going to do it for lambda equal to 0, assuming the matrix to be invertible. But the answer is yes. We're going to derive it just because you see it. Okay.
Is that a small xt?
Here
Yeah.
is any row of this matrix, or in other words, any input points. Okay. And in this case, it's not any. In the sense is, you pick an order. Okay, which in this case is fixed a priori. It might be the order in which they arrive, or in the order in which you decide to visit the points sitting on your hard disk. You see the first one, the second one, the third one. You never see the same point twice. Pick an order, go to the end. When you're done, you compute the solution. Okay. Yeah.
Isn't xt is a row or a column? A column.
Xt are the rows of. These are the rows of the data matrix. So each xt. Sorry. Yes, that's correct. Each xt is of size d, right?
And it's a row.
And it's a row. You know, it's good to always double check. You have n rows and d columns, and each row is length d, the same length as the vector of coefficients. So this is a number, okay?
And if you put in that diagram there, that cartoon, you would write xt transpose or xt? It's a call like.
Oh, I suck. I don't know. I would call this xt.
Okay.
And then I. This is the way I would put it to get the right thing there.
Okay. I'll mess around with it.
Okay.
I'm just trying to get the dimensions down here.
So the dimension is.
Scale, like, I know things.
So this is, yeah, you're right. Probably I should do it the other way around. So I'm very bad with that. This is the important thing is that this is d. I don't know if I want to put it as a row as a columns. I guess I don't know. It's too hard for me. But this is is a d-dimensional string. This is a dimensional string. Then this is a number.
And things add up as they should.
Yeah, they do.
Cool.
I have a problem with transpose. Was another point? Yeah.
So is gamma like sigma inverse times x hat?
Yeah, that's what we want to do next.
Okay.
Yeah. Yeah, you can kind of get what you kind of are doing is start to stare at this and say, where is this coming from? And it basically comes from this sigma, and that's the reason why you use a symbol for it. Okay, I mean that's what we're gonna do. It's relatively simple. Okay. I guess the one observation. Any more points? I guess the one observation we can make is that this algorithm is online in the sense that it gets data and adapts. What is the memory cost of this? What is the time cost of this? So essentially, this doesn't cost much, right? What the main memory cost is for this matrix here. You have to keep it. Notice that it's constant. You add more data, and it doesn't add up. You just store in memory a d by d matrix if you want to keep it computed all the time, and just keep on doing it. So it's a constant time algorithm, and the cost is going to be essentially these vector matrix multiplications, okay? And as many as the number of steps you do, okay? And you can check that essentially this is going to be the same cost of performing this thing here, okay? So this thing here at the memory cost, which was nd to to initialize this matrix. Then you have to compute this guy and this guy. And at that point, the cost would be just nd plus d square. And then you have to solve this system. And this is going to be nd squared to build the matrix, time, okay, plus d cube. So this is memory and time. The cost of this is going to be essentially d squared in memory, and then it's going to be the same as that, nd squared. The difference is that here, if I want to go from n to n plus 1, unless I play some trick, I have to recompute the, I have to reinvert the, I have to rebuild the matrix and reinvert the matrix. Whereas here, I just go from this step to the next one, and that's it. Okay? There was a question somewhere.
Is the denominator, like the 1 plus xt transpose, and the next thing, should it be t minus 1 or not? The subscript for the...
Here.
Yes.
Yep. Yeah, it's a recursion. Thanks. Yep.
How to initialize it?
We have to check. I think you just have to take the identity here and the 0 here. Well, you can do whatever you want, but that's a basic one. Okay. I think I was trying to remember, but I don't remember. But I think we're going to see it as we prove it.
During the update on W, gamma t is a matrix.
Yes.
And xt is a vector.
Yes.
And the stuff after is also a vector.
No, this is a number. This is a number. Yt is just an entry of this vector. So y. Okay, so we're going to use this in a minute. This is going to be sigma 1, and this is xt from 1 to n of xt yt. Number, okay, vector. Okay, this is a number, and that's like the whole point. This has to be a number, okay, and this has to be a vector. We don't want this to be a vector and this to be a matrix. Otherwise, this would be it. Okay, this would be the batch gradient. Okay. Yep.
So for the only gradient to converge to the batch gradient, are there restrictions on like how the xt's are?
Yeah. So let's wait a minute because. So the question is, what about convergence? Okay, and we're going to see that we're doing something super simple in this case. We are rewriting the solution. So at every step n, okay, this is the same as computing this solution here. Okay, so it's not quite that it converges; it's just that you get the right thing. Okay, when we actually do to the full-fledged stochastic gradient, we're going to remove this matrix and replace it with a constant. To really have a linear order memory algorithm, in that case, then we don't know anymore. Okay, we have to prove that it converges somewhere. In this case, it's just a rewriting of the solution in a smart way. So it's the right thing. It's actually just another way to compute things. Okay. Right. Let's do it.
So after doing this for every point, it's like doing the same thing on all of them?
Right. So actually,
okay.
Doing this after 2 points is the same as doing this with 2 points. With 3 points, 3 points, and so on and so forth. Okay? There is a one-to-one correspondence. And the proof is elementary. It's just a sequence of observation and a couple of linear algebra equalities. So the first observation is the W hat lambda is this sigma. So let me emphasize the dependence on the cardinality again. Okay. So W hat lambda with n points is going to be sigma n to the minus 1 sum of xt, yt, t from 1 to n. Okay? And if you wish, I can write this as sigma n minus 1 sum t from 1 to n minus 1 xtyt plus xdyt. Agree? Then let me write w hat lambda n minus 1, which is simply going to be maybe let me tell you where I'm going with all this story. We're going to write the solution. We're going to write the solution with minus 1 point. We take the difference, okay? And then we elaborate a bit on this difference, okay?
And this term be n instead of t?
Sorry, this is be n. Thanks. Okay, it's the last one. I just factorized out the last one, okay? So now that you see I'm going to have one term which is very similar in both, okay? Then what you do, you take the difference, you elaborate a bit, and then you write this in terms of this, and you get the recursion. That's what we want to do, okay? All right, so that's step 1, okay? Which means that we can write w hat n lambda minus is equal to okay, then I have, so I wrote this one first, and then I have this minus this. And I can factorize the two matrices, okay? I can just pull them out, okay? This is the first time we use a trick. If you have two matrices, A minus 1 minus B minus 1, how can you write down the difference between the two of them? If they were numbered, what would you do? You would get B minus A, say, divided AB, if these were numbers. But these were matrices, okay? So you have to be a bit careful. You cannot just divide by a matrix. So it turns out, but we're going to check, that this is, well, I don't remember, so we're going to do it. I never remember the order. So we want to prove something similar to that with the right order of the matrices, okay? So what do? We say A minus 1. Oh, of course, I'm assuming that everything is invertible, okay? And then I write B minus 1, B minus 1. And then I factorize out the B minus 1, okay? Then I play the same trick here, and I write the identity as A minus 1A. And I skip one step in here, okay? So I wrote the identity as A minus 1A, and then I factorize out A minus 1. So I get A minus 1, B minus A, B, okay? If you now take A equal sigma n minus 1, and B equal sigma n minus 1, sigma n minus 1 to the minus 1. Yep.
Why do you have to the minus 1?
Where?
That you have like, if you're doing A minus 1 to the B minus 1, then you already have sigma to the minus 1 to the left.
Sorry, you're right. Yeah, right, you're right. Here, you're right?
Yeah.
Okay, and and we can just plug them in, okay? And that's what I'm going to do. Before we do that, let's just notice that if you do the difference between these two, remember that sigma n, let's write it here, sigma n is just the sum of xi or xt, t from 1 to n, okay? Is the sum of outer products of the rows. So we can now write down explicitly what is the difference between minus 1. What is it? The difference between the matrix where we sum up n minus 1 addend and the one where we sum up n addend is just going to be minus xn transpose. Okay? So now we take that expression, we plug it in here, and we see what happens. Sigma n minus 1, xn yn plus, so what do I get? I get sigma n minus 1, and I'm happy because I see that I have the same thing in front of everything here. Then I get minus xn transpose, and then I get sigma n minus 1 to the minus 1 sum t from 1 to n minus 1 xt yt. What is this?
Wn minus 1.
It's just wn minus 1. It's written here. Okay? So no, let me do two things at the same time. Okay? I'm going to factorize this and also carry on an xn because there is an xn here and an xn here. And then I just write this as wn. So I get okay. Yep.
In brackets, you had sigma n minus sigma n minus 1.
In where? In brackets?
In brackets, like third, yeah.
Yeah.
But then you substitute sigma n minus 1 minus sigma.
We did it.
Like the last line on the right board, it's sigma n minus 1 minus.
Because that's what I get from here. So if I do a to the minus 1 minus b to the minus b, that's exactly why I had to do it. I always forget this. They swap. This, you get the b coming out of here, but the order swap. Okay. So here, this one is sigma n to the minus 1 to the minus 1. And there is and I think I'm screwing up the indices, right? Because what we get here is xn minus 1. So this should be, oh man. Oh, let's do this. Okay, so I just want to get I want to have the indices right, okay? We're getting the right formulation. There was a shift of the indices. Now that's fine according to this, okay? It's just a convention. We want the indices to go the same way. Is that okay? So far so good? We're almost done, okay? Well, we're not done yet. Because here, we're still going to have a recursive formula for this matrix here. And the guess was right. The gamma that we have in the other plot should be essentially this. But we have to find a way to be able to somewhat compute this also. So this is a rule that says if you have access to this matrix, then you can update the solution to go from n minus 1 to n in a recursive way. Okay, in an incremental way, one new point at a time. But here you still need to find something that is going to allow you to update this. Okay. But that's easy because it's essentially just a straightforward application of Sherman-Woodbury identity for matrices, which is exactly one way to update a matrix given another matrix. Okay. This is tedious, so I want to write it right. So the Sherman-Woodbury identity says that if you have a matrix A and you have another matrix that you already, the idea is you have a matrix A, yes.
Minus A, what happens with the extra lambda?
I just put lambda equal to 0 for now, okay? That's I just want to simplify notation, so we're just orienting with lambda equal to 0, which is tricky because at the beginning it will not be invertible. Let's assume that you start after a few steps, okay? Otherwise, you just have adapted and you're going to get an extra few lambda. So the question is, what happened to lambda? I killed it at the beginning because I just want to simplify the notation, okay? You essentially would have an extra lambda appearing in a couple of places. Okay. So back to the story, we want to try to find an equation to update the inverse of the matrix. And just remember that we have one identity. The Sherman-Woodbury identity allows us to do just that. The idea is, imagine you have a matrix A that you have already inverted, and now you do some kind of an additive update of this matrix and you want to invert it again. Okay? For us, this takes a particular simple form because it's just going to be a rank 1 update. We just want to add an X transpose, and that's it. Okay? But the equation, the identity holds for more generally. So let me write down the general expression. The general expression is a to the minus 1 minus a to the minus 1 b. Then there is a dA minus 1 b plus c minus 1 dA minus 1. Okay? And then for us, we just want to apply this with A equal sigma n minus 1, B equal xn, C equal 1, and D equal xn transpose. Okay? Yes?
Minus 1.
D minus 1, there is a minus 1 here. That's a 1, right? Yeah. Thanks.
C is a matrix, right?
In this case, C is going to be just a number. These have to be matrices, okay? But in our case, they are going to be vectors. So that's a matrix with just one dimension on one side. And so it means that this matrix that has to be of the same size of B on this side, and D on that side is going to be a number. D by 1, 1 by 1, 1 by D. It's a very small matrix, it's a number.
So where do we see this form? A plus, is it this?
Sorry?
The form A plus BCD, where...
So what I want to do is that I want to write down sigma n minus 1, okay? Which is equal to sigma n minus 1 to the minus 1. Sorry. Yeah, so okay, this is fine. Okay, so I want this, okay? The matrix sigma n is equal to this, okay? And then this is why I want to do this, okay? A, B, C, D, okay?
So A is just sigma then?
Sigma n minus 1.
Yeah, without the minus 1 on top. Not inverse of.
Sorry.
Yeah.
Yeah, thanks a lot. And we're done. We're finished, okay? This gives us what we want. This is exactly the same as the equation I deleted was written here. So this is going to be equal to sigma n to the minus 1 minus sigma n to the minus 1 xn. Then that's just a number. For us, this is just going to be a number. And it becomes 1 plus xn transpose xn transpose to the minus 1. Okay?
Sigma n minus 1.
Everywhere. Okay?
What happens if you initiate a matrix differently instead of identical matrix?
Let's see. So I don't know. I mean, I haven't thought about it before. I mean, somebody else maybe will see it better than I do. I think what's going to happen is that you get a matrix and you're going to shift it. Let's say that you're initialized by a diagonal matrix. Okay, then basically it means that you're going to shift by whatever you put on the diagonal. So in some sense, there's some kind of preconditioning / regularization associated to it. I don't know. I haven't thought about it. I mean. In this case, I really stuck just to the idea that this is the computation of the solution of the regular least squares. Okay, this one here. And again, I killed lambda to make notation a bit simpler, but you can plug it back in and track where it appears. The idea remains the same. Is that okay? Yep.
General question: What is there like an intuition for why you go through why this adaptation works in online learning, or like why you make this adaptation generally? Because it makes sense that it like equates.
So this is very special for least squares. So, or there are a couple of other algorithms where it works. Okay, it's just a specific case of there, and it's very specific because it's not quite. Again, it's an online learning algorithm, but it's not. It's a bit of a nice stochastic gradient algorithm in the sense that you have a stochastic gradient in the sense that the gradient here is just an estimate of the gradient, whichever you have in your mind, the true one or the empirical one. But then you give yourself room to use this big matrix valued step size. And what you get out of it is that essentially you converge, okay? And in the slides, Sasha last year pointed out a connection between these as a Newton method, where you actually have an exact computation of the second derivative. You can interpret this as to be related to the Hessian of the problem. And so you basically say, I'm gonna, Newton method with an exact second order method is gonna converge in one step. And that's basically what's happening here. And then you just update, okay? So in some sense, this is a very specific case. It's just that it's, it takes, 20 minutes to introduce it. And then you learn a couple of very basic identity. And you got a feeling of one idea or how to get a recursive iteration in the case of least squares. Okay? Yep.
So in this case, the gradient descent is somehow giving us the exact optimum.
Say it again.
The gradient descent algorithm is giving us the exact minimum.
When you say gradient descent, you mean this iteration we derived?
Yes.
Yeah. So let's call it recursive least squares. It's not a gradient descent of anything. It's a recursive formulation of least squares that is equal to the solution of the problem at each step for increasing number of points. So it doesn't even converge, it's the same as. Okay? All right, so what did we find out? We discovered by simple linear algebra a basic online algorithm in the sense that it's incremental. It updates the solution at step n-1 where you receive a new point without recomputing things from scratch. If you want to study any property of this algorithm, it will be the same as studying the property of the exact ridge regression empirical risk minimization estimator, because they're the same. At every fixed number of points, they're just the same, okay? If you want, there are a couple of outstanding questions here. One is, okay, can you do something for a loss which is not least squares, okay? And even more, can you do something where you don't have this overhead of having to store a full matrix for the step size, okay? And so basically that's what you do when you start to look at the, the basic stochastic gradient iteration. You, instead of using the iteration we just considered, you look at something like this. Okay, so let's say we had the big gamma t here. I'm screwing up signs here. I don't remember which one is correct. I think it should be like this. So this is the one we just derived for least squares with this gamma. Now what we want to do is that we want to replace these with a sequence of numbers, okay? So this is just a number. Of course, now we cannot hope anymore. All the question you asked me, does it convert? Well, now we don't know, okay? It's no longer a representation of the solution after seeing t points. We have to figure it out. On the other hand, we can also recognize that this is just the gradient of y t minus w t xt minus 1 square, okay, 1/2. And so now we can write down, more, for any loss function, we can actually consider something like this. Oh, let me write it. Okay, I'll just write it like this. Okay. At every step, you have access to the gradient of the loss function at one point. And then you update your solution. Okay? If you wish, this is the case where L is differentiable. If it's not differentiable, you can replace this with some element gt that belongs to the subgradient of the loss at that point. Okay? As we did when we moved from logistic regression to SVM. Okay? And you will have all the same problems, which one you pick and so on, but the story is the same. We covered it already, there's nothing to add. The big story here is that, again, compared to what you had in the classical gradient descent or stochastic gradient descent iteration, rather than just a simple stochastic gradient, what you would do is that you would sum up the stochastic gradients. Okay? So what you would do is that instead of just doing something like this, what we did before was actually waiting to compute them all before updating our solution. Okay? So the difference should be clear at this point. In one case, I receive the same kind of gradients, I compute all the gradients, and then I update my solution. In this case, every time I receive one gradient, 1 point, I update my solution. Okay?
So this is what you call the stochastic?
Right. So this is what you call, universally in machine learning, it's called SGD. Okay? And it's called SGD even when you use it in this case. So stochastic gradient descent is the running name. Notice that, to be more precise, is not a gradient of anything if the loss is not differentiable. It's a subgradient. And it's never a descent method. Okay? So if you would call it stochastic subgradient method, would be the pedantic correct way. But SGD is short enough. So we're going to use the same name that everybody uses. Okay? But it's not a G and it's not a D. Okay? It's just an S. All right. So no, now this is what we want, right? This is an update that just uses constant memory. This is a number, just matrix vector multiplication. The cost in time is just going to be a vector multiplication at every step, okay? And then the storage time is just to compute. If you compute the gradients on the fly, make a multiplication, throw it away. In memory, you just need twice the dimension, okay? You really don't want to do this, but this gives you a feeling that you don't have to store it in memory. You have to decide how you want to use memory. Okay.
How did you choose gamma t?
I didn't. The question is, how do I choose gamma t? And I just wrote it, okay? I just wrote it there. I call it gamma t and I did it, okay? Now, how can you choose it, okay? You can choose it in a couple of different ways. One way to do is to decide what is the objective of this and study its convergence and then derive a choice that is going to ensure convergence somewhere. Because again, it's not for free anymore, okay? Now that we replace the big gamma with a small gamma, we doesn't even know if it converges, okay? Yes.
So
we're going to do it. Now I'm going to show you.
I imagine you can also extend this if instead of just one single data point, you receive a whole bunch of them.
Right, right, absolutely. So let me write that, which is more interesting than the proof. So in practice, you don't do this, okay? Unless you receive 1 point at a time, wait one night, and you really can do nothing immediately. You never do this, okay? What you do is that you do mini batching, okay? Okay, notice that here I just did this as if you're doing just empirical risk, but you should really think that here you have an extra plus lambda t, okay? You just have always the extra regularization. We're going to we're going to view this as an optimization method, okay? So we always have the extra regularization. In this case, it's easy to add it in the notation. So what is mini batching? It's tedious to write, but obvious, okay? What you do is what you just said. If B is the size of a batch, so you're going to, instead of instead of picking one point or all of them, you pick the one that you can handle, fast enough, and you called it a mini batch, okay, of size B. B is the cardinality, so it's going to be some subset of the points. And then what do you do? Okay, it's going to take me a minute to do this. So I think it's B t minus 1 plus 1. I always forget. Should be like this. And then here you just do gradient of L, Yj, Wt, Xj plus lambda t. Okay. I just wrote what you said, okay? And every step, what you do, you take a bunch of points, okay? You use them, you compute the gradient, okay? And you can do this for a couple of different reasons, okay? Well, I tell you three, well, I'm gonna forget them, so I'll tell you one and then I see if I remember the other ones. You want to make better use of your memory, okay? You have a certain amount of memory and you know that, accessing the disk and the memory is gonna be costly, so you just wanna do it a few possible number of points. So clearly picking one point at a time is insane, okay? That could be one reason. Another reason could be intuitively, albeit we're not gonna really look at this. This is gonna be an estimate. The idea is that this is a stochastic estimate of a gradient that will be the right one, that either we cannot or we don't want to compute. This one is a gradient that we don't want to compute, okay, because it's too long to compute, but we can also view that as a gradient of the true risk, okay? A stochastic estimate of the true risk. And that one we just cannot compute if the distribution is not known, okay? In that view, here, perhaps I'm doing a better estimate of the gradient at each step, because rather than just using one point, I'm averaging out over a bunch of points. So presumably this is going to be still a stochastic estimate, but with less variance, okay? And you can hope that at some point, the variance of your gradient estimate is roughly the same order of the variance and the noise in your points, and so you don't need to go full-fledged GD, but also you can do much larger than just using one point at a time. And indeed, this can be proved, okay? The last point, if you want to parallelize, okay? If you want to somewhat split the computation, you can do it here, right? What you do is that you send a bunch of data points to a bunch of different processors. Each one is going to compute a piece of the gradient. They send it back to you. You update your solution. Here, you can actually try to do something a bit more refined, because essentially what you do is that you can now, this is the first step in try to say, okay, each one is going to compute a piece of the solution, and then I update the solution combining them in some way. Clearly, this is much harder. This goes into distributed computing, because it's not just a fully centralized update, but each one can make its own update, okay? But if you look at, there's a lot of studies you can imagine in try to distribute the computation of a gradient over a network, and if you want, this is a first step to go in that direction, okay? So definitely this is a good, this is a typical variation over the theme, okay? And again. And the last one I wanted to mention is the last trick that one does, is used a lot is what is called the accelerated version of stochastic gradient descent, okay? And there is a zoo of possible variation over the theme. And I just mentioned, because it's popular, the momentum method, in particular the momentum method inspired by Nesterov acceleration, which is basically based on the idea that rather than using just one, the previous iteration, I use the previous one and the one before, okay? So I use two previous iterations and I try to combine them to get the best. Okay, and the idea is that in some sense this is a second order term. It's a kind of inertia, okay? Acceleration term. One is the velocity, this would be the second derivative discrete of the velocity. So in some sense you can view it as an acceleration term, okay? And try to make this, what I just said, more precise is tricky, but the intuition is pretty simple. And the algorithm to write down is simple because it's the same as before, with just one difference. So this line is the same as that. The only difference is that inside of the gradient, I'm not putting the previous iteration. I'm putting another vector. I call it Vt. Vt is going to be equal, this is one way to write it, so this one is not so important. The main point is that this is essentially a combination of Wt and Wt minus 1. That's what you have to read from there. Okay? So you don't only use Wt, you take Wt and you try to find a good combination with Wt minus 1. And then, of course, you can ask yourself what is the good way to combine. And this is the classical one that comes out for studying gradient descent for Nestor acceleration. Yeah.
Should that be Yt and Xt in the same class?
Well, I'm writing it in the same, I'm trying to keep, so what he's asking is what about t minus 1? It's just a convention, okay? I'm just following up with what I did before. In some sense, when you do the recursively squares, it turns out that the notation I'll be using was essentially calling the example instead of 1, 2, 3, n, calling them 0, 1, 2, 3, n minus 1, okay? And now, when you prepare the class and you should check this stuff and you forget that detail and then you have to carry on and it's a pain. Yeah, that's what happened there. But it's not so important. There is just a shift by 1 everywhere. Hopefully it doesn't create too much confusion.
So beta is a constant?
Beta is just a constant here, okay? And again, don't focus on this too much. This is one possible choice. You can do other stuff. There is a whole thing. For mod matters, I wrote this one just to show you that it's not just any crazy choice.
Why is it going to 1 as t goes to infinity? Shouldn't it go to...
I don't want to discuss that at all, okay? If you wish, I want to do this, okay? I put it there just that you see that it's not just crazy thing, okay? Now it's gone, so we don't have to think about that. And this, well, maybe the one thing you want to think about is that this is called the momentum. Okay? That's the momentum, okay? Which is this difference between the previous and the previous one, okay? And this is just one way to use the momentum, okay? If you look at the literature, for example, another classic way is the heavy ball method, okay? Which is related to Chebyshev iteration and so on in the case of least squares. And these are just different ways. So the main point of this, we're not going to study any properties of this. I want to tell you a couple of different flavors, okay? That are very common. I would say that combining these two things is a very common practical thing, almost to the point that when you actually have to deal with very big data sets, you kind of have to do it. Otherwise, it's going to be too slow and too inefficient. Okay? The reason why I didn't want to discuss this is not because it's not an interesting question, but it's just that in the case of stochastic gradient, it's much more, it's a little bit tricky, okay? Essentially, the original idea from Nestor were just for basic gradients, and there is a proof that is what we consider to be complicated and not very transparent in the way it works, okay? And then when you go to stochastic gradients, things get even more tricky because in some sense the effect of acceleration is a second order effect. It doesn't really go faster in terms of convergence. In some senses the area is sum of two terms and one of them goes faster, okay? So in some senses, and this is like, what people have been studying and are studying now, okay? So I don't feel like there is any super insightful basic thing I can say about that choice, okay? All right, so what didn't we do? What we didn't do at all is try to get a feeling of why this converges, okay? And it turns out that the proof, again, you can do a lot of different proofs, but one basic proof is the one for the subgradient method. You remember last class I showed you the proof of the subgradient method, okay? Turns out that you can basically do the same proof. The proof is relatively easy, it's just a few lines. And then basically, if you just take expectation on both sides, you can now account for the fact that the gradient is stochastic. Before doing the proof, let me emphasize a bit this stochastic gradient aspect of this story. Okay, particularly here, I just throw there in the discussion before that I can view this. Okay? I'm going to use the notation as if it was differentiable to make it a bit shorter, otherwise I have to do it all the time. Okay? So you can view this as the gradient of a couple of different things. Okay? You can view it as the gradient of the empirical risk or of the expected risk. Even before trying to prove anything, let's make this precise. Okay? So, where do I have it? So let GT be the gradient of L at YT W transpose XT. Okay? Then if you take the expectation of GT, which is expectation over what?
X and Y.
YT, XT, and for now I'm picking W fixed, okay? What is this going to be? You have to take the expectation of this quantity. You can now swap the derivative and the integral, and the expectation, the integral, and so what you get is that the expectation of delta L YT W transpose XT simply becomes the gradient of L YT W transpose XT, but this is what we call the risk. Of W, or if you wish, of okay? So we can view that thing that we use at every iteration as a stochastic estimate of the gradient of the expected risk. And in this view, we can now see that if you ask where does that iteration converges to, it's going to be the regularized expected loss, okay? Because we added that plus lambda, okay? It's going to go not to anything empirical, but the true one. And in that perspective, we need, so this is done for every new point, okay? Consider now the case where you want to put, in place of W generic, the WT that you computed up to that point, okay? So what you see there, and maybe now it's kind of useful to have used a different notation. We have each gradient is W, in that case is WT, and then I use YT minus 1, XT minus 1, okay? So think about it. This guy is going to have seen all the point. If I put here WT, this has seen all the point up to the last one. So it has used all the points up to the last one. And then I obtain the last one and update. Make sense? So this notation use all the points from 1 to t minus 1. And then I receive the new point and I compute the gradient. Which means that I have to be a little bit more careful here, and I have to condition over WT, that is over the past. But then the same results hold. Oops. Is that clear? Again, WT uses all the points up to t minus 1. Okay, then he receives the new points, and then you compute the gradient. So WT has knowledge of the past, but the new points arrives. Okay, so if you condition over the past, if you assume the data to be IID, then this is going to be true. Okay, it's as if I'm taking only the expectation over the last point, because everything decomposes nicely. Okay.
But how would you compute this gradient?
You don't compute anything. I'm just showing that the one you have in practice is, so the question is how do you compute it? You don't. What you do is that you show that this one that you compute, how, this way, is an estimate of the true gradient, which is what we prove right here. So you just give right to the name stochastic gradient, okay? And it basically shows if these points are randomly sampled from the same distribution. So if xt, yt come from the distribution pxy, that is the same as distribution with respect to which you take the expectation, then there is a stochastic estimate of the gradient of the expected risk. Okay? So it's not just this is not a computation, it's just a justification for the name stochastic gradient, and the idea that you can now apply this method to solve this, which is what is called the stochastic optimization problem. An optimization problem where the objective function is an expectation, and what you have access to is not the gradient of the objective function, but some stochastic estimates, okay? Which is exactly what we have here. And note,
what I meant is
okay.
by the time you're doing this, you only have WT minus 1. You don't have
When you do what? This or this? Because this is the only computation that exists, okay?
Right, but you're writing g of t as a function of WT. But at time t, you only have WT minus 1. Unless there's something.
Again, I mean, let me just, because I may be screwing up.
Maybe I'm wrong, I don't know.
Is that again, the problem is that I'm getting confused with this notation because this is even more confusing, okay? I'll use that notation, but it's even more confusing. Let's see this is what we do there, so let's be consistent, but let's see what it means, okay? Let's see what it means. It means the following. I initialize with W0, okay? No, and I've never seen anything, okay? Then I get the point, and then I update my solution, okay? Then I get another point and update my solution, okay? So the gradient always uses the previous solution and the new point to update the solution. You pick a solution, you use the new point to compute the gradient, and then you update. At the next step, this solution have seen the previous point, but clearly have not seen the new point, because you use it to update and get a new solution. Make sense? So the W have seen the past, the new point is the new point. Okay?
So the y and the x should be plus 1.
Well, that's the point. I mean, it's just a convention, and this is the convention that came out of recursive, okay? And it's not about, imposing what you like. That's the correct one, is the one that came out. The point is that you have to do the right ordering, and that's what it means, okay? That's what it is. If you want, this is really confusing, I agree, okay? It should be the other way around, but that's the one we used up to this point, so we just have to interpret the one we used. The important thing is that's what it means, okay? It means that WT has access to the past, and YT, in that case, -1 is actually the future, which is, I agree, is confusing, okay? But that's the main point here. Yes?
How did you remove the conditioning in the last step?
Say it again?
How did you remove that conditioning in the last step? So L is the expected value without the conditioning, right?
No, you can put it back. So sorry, here, because I absorbed it here, if you wish. No, you're right. Let's leave it. So this would be. You want to do this? Sure. Yeah, you're right. Okay. Okay.
But this is not a good estimate of the gradient.
Is the estimate you get at every step, which is an unbiased estimate if, again, in the IID case.
What you want is the expected value of L, right?
I'll think a second about it. I'm getting confused now.
I think the last line you should not put it because.
Well, so I don't want to have an open discussion on the result, which is a proof. It's just that I don't see it and I have to do it, and I prefer just to think a second about it and come back to you. Okay? I think you're right. I think it should be. I'm getting confused now. I think it should just be the gradient, but I don't see it right now. Let's just leave it right there. Okay? Because what I want to show is that this is just one of the two possible stories that you can attach to that iteration. Okay? This one is the one where you see the gradient as a stochastic estimate of the true risk. Okay? Let me fix that. And then the other one is the following story where you really take a kind of different point of view. Consider now this, okay? The empirical risk. If you wish, you can write it as an expectation over what? You take expectation over a random variable, which is uniformly distributed over the indices between 1 and n, okay? So you pick a point, we pick an index uniformly at random between 1 and n. Okay? So you pick a point uniformly random between 1 and n. Okay? And that's your variable j. And then you take the expectation with respect to that. It's uniform. So every index is going to have the same weight. So it's going to be exactly the one above. Okay? It's a measure that is supported just on those n indices, which are those n points. Okay? It's just another distribution. This is a distribution over x and y, which is what is the support of the distribution everywhere. It's every point in the in your input space and the output space where there is non-zero mass. If you take the distribution instead, this is just supported, meaning that it has non-zero probability on those n points. And each one is equally likely to be sampled. Okay? Now, following a similar reasoning, if you now take So think about what you want to do right now. You have n points. You pick one uniformly at random, okay? And then you do the expectation over sampling that point. Again, it's going to be the 1 over n, okay? Sum of all points. And you find out that this, if you see what I'm saying, you just pick a point uniformly random between 1 and n, and then you take the gradient of the corresponding loss function. If you take the expectation, this is exactly the gradient of 1 over n sum okay is the same as before, just for a very specific distribution. It changes dramatically the way we think about the iteration and somehow the way you use it too. In the first case, the idea was at every step I pick a new point, okay? And every time I pick, it's a fresh point. It's not, I never look at the same data twice. Imagine that you have your data sitting on your computer. If you want to use the first observation is pick a point, do a step, pick another point, do a step, pick a second point, never pick the same point twice, because they have to be identically and indeterminately distributed between each other, in particular independently, to use that reasoning of before, okay? And then in that case, you could prove, okay, or the idea is that you can view the gradient as a stochastic estimate of the true expected risk gradient. In the second case, the idea is you have the data sitting on your computer, you pick one at random, and then you put it back in, okay? And then you pick another one at random, and it might be the same guy, okay? And you keep on going, which is typically what everybody does in practice, okay? Because why shouldn't you, okay? And if you do that, there are a couple of differences. One is that now you can pick the same point multiple times, which also means that you can do more than n steps if you have n points, okay? You can do n steps, which is what you might call the epoch or a pass over your data, which is on average looking at each data point once. But once you've done once, you can keep on going, okay? And in that case, as the number of iteration goes to infinity, the idea is that you might be converging to this kind of quantity, okay? So the first one is sometimes called a single pass SGD, the idea that you use one point at the time and you're shooting for the expectation. The other second one is sometimes called the multi-pass SGD, where you look at each point multiple times and then you converge to something like this. Okay? In this second view, clearly you have other options, right? This is uniformly at random and is the one that comply with this derivation. But now look at this, okay? And view it as just something that is access to the data points. Can you think of other ways to access the point instead of uniformly at random, I never remember with or without, putting it back, okay? What could you do? Well, for example, you could pick a point, use it for your iteration, and don't put it back, okay? Which means that what might happen is that if you don't, you can do different ordering in different passes. You can still look at the same points more than once because you can do multiple steps. And this is sometimes called the reshuffling operation. It's equivalent to take the data, fix an order, do a pass using one gradient at a time, and then reshuffle the order and then do it again, okay? Or you can just fix an order and go for it, okay? This is what is called incremental gradient. You pick an order and you go for it and you just do the data multiple times. So you're gonna see the first point and every times after n is somewhat a periodic way of seeing the data, Okay? And these are all different flavors of so-called incremental gradients. And if you navigate the literature, these two things are somewhat, from a practical point of view, you do whatever works best, okay? But in some sense, there are really these two streams of literature. One was the goal is optimizing this, and where the goal is optimizing this. I blabbered enough not to have time to give you the proof of this, but essentially the proof is, let me just write the statement of the proof, okay? The statement of the proof is simple, okay? And it simply says, suppose that you have W star, which is the minimum of a function f, okay? And then define Wn to be just the average of the iterates. Okay, the result is not for the last iterates. Classically, you have to consider an average or the best of the iterates because the method is not a descent method. So you have to be sure that something nice happens. Then you can prove that, and I'm assuming f to be convex with bounded subgradient So there is a suitable constant so that if you choose gamma t to be constant over square root of t, which is exactly the choice I showed you last time, then similar you get that this goes as, sorry, let me do this. Okay, so that we make clear that this has nothing to do. Okay, so this is the same result we used for the subgradient for SVM, okay? The proof is both in the slides and in the notes. This is one of possible proofs, the one where you only assume bounded subgradient, okay? That's the only thing you assume. You can make it stronger in many possible ways, and this is the same one I mentioned last time, the one where you take a decaying step size that account for the non-descent properties of the iteration, okay? And then here I unveil one detail that I didn't write the last time, which is that for this method, the classical, you can actually prove things for the last iterate, but it's much more complicated. If you actually consider the average iterate, not the last, but the average of all of them, the proof is just much easier, okay? And so that's the one we put in the notes, yeah.
Shouldn't we put an expected behind that?
Sure, sorry, yeah. This quantity. So the point is that, so this, the proof, look at the proof for the Stochastic subgradient, okay, which is this. And basically, as soon as you put a conditional expectation, like that one, on everything, the proof remains the same and goes through for the subgradient, for the stochastic subgradient, okay? So look at the standard subgradient once, because the stochastic subgradient is essentially the same with an extra expectation, okay? Things behave very well. Yeah?
The statement is that such a constant exists?
The statement is that the constant is the Lipschitz, it's explicit. I'm just not writing it now. It's basically the Lipschitz is the bound of the subgradient and then a bound on W star. Yep. So, but I'm done in the meantime. If you want to escape, you can.
Doing random properly, is there like any bounds that?
There are bounds that show that it converges. And it's not completely clear how much better or worse it converges with respect to random subsampling with replacement.
Oh, there's a bound.
There are results. Yeah, results exist. Yeah, well, I can give you a name.
When you